So I like to separate swap IO from the memory utilization. Again, I do advise having swap on, having a swap. In fact, there are sites, HLRN and stuff, that have a very, very large swap. Now, what was the reason that I said that I wanted a swap?
It's better than the killer.
Correct. And one of the key things that I tried to describe yesterday is if I don't have swap, the memory growth intensity is so fast that in this example at one site, 3 jobs submitted, each contained within a CPU set, but then trying to do more memory than the CPU set, they would all hit at the same time. Once you added in swap, the swap IO would throttle back the intensity of the memory growth, and it would do it unevenly. So in the memory lab, when I was trying to push to I have you take swap off because it's easier to hit Once you add swap in, they don't all grow at the same rate. So when they get its full memory size, finish and go away before the other one starts growing again. So by having the swap there, the swap IO is going to reduce the memory intensity, memory growth intensity, spreading this out unevenly, resulting in the operating system kind of working itself out. Does that make sense? So there are sites that use swap as a way to throttle back things. Oh, I never did get to this. Let me do something here too. Mike had a question in this area. I'm going to go to Floyd 3. So there are sites that, and NASA Ames has one of the code examples they wrote, which is a daemon that runs and watches CPU sets. And there is a memory pressure enabled. Let me just cap that thing first. It's a 0. Oops, I want the enabled one. It's a 0. I'm going to echo 1 into this. So this is what NASA Ames was using. And that memory pressure field will not start growing. It will be 0 until I actually hit a memory pressure situation. So memory pressure doesn't start counting until you actually have a CPU set that is starting to swap. Now let me do an LS on dev.
We can't see that desktop, Dave.
Oh, I'm sorry. Thank you. So I basically logged into Floyd 3, into dev CPU set. There's this memory pressure enabled, and then there's the actual value, which is really just a memory pressure intensity type of number. Now I've got a boot and a login, and I got a PBS Pro. I'm going to go into PBS Pro. No jobs running right now. I'm just going to create a directory here, make dir DAW. Let me just cat for CPUs 4 through 31, 4, 5, 6, 7. Okay, so I'm going to go into DAW. I'm going to echo 4 to 7 into CPUs, and I'm going to echo, let's see, that should be node 1, I think. Let's just check here. CPU map, 4 through 7 is the second socket, socket 1. Again, these are within the system, not offset to the partition. So I'm going to take this as my CPU set for this example. So echo a 1 into MEMS. Now, notice that there is no memory pressure enabled in the individual CPU sets. That's only in the top. It's only in the top one, and I've set that to a 1 right now. Okay, now let me echo $$ into tasks, okay, PS, cat tasks. So there's my shell, and all children inherited are in this CPU set. Now let me try doing a, this is, where were we on sizes? We don't get it here. Let's do an N info. And I'm on node 1. This should be where I am here with node 1. I got about 33 gig. So let me try a memhog 40 gig. I don't think this will work. Oh, it's working. Now, let me just break out a second. Let me put it in the background here. I'm actually going to fire up a couple of them here. Now if I do a watch on memory or cat memory underscore pressure, and we've got a number going on there which tells me that we're swapping. So this daemon thread that NASAIMS run is watching that and finding the CPU set that has that number growing. And then that's what it targets. It figures out what PIDs are in that CPU set. Let's do a SAR-W, 1-4, wrong. So there we can see the swap outs going right now. And info. And I am in the same CPU set, so I am competing with it. And there we're down to 29 meg free. And all of it being anon pages from memhog. SAR-S, 1-4, see where we are. We're at 76, 77, 78. Let me bring up a top, see if we can catch it here. So there's the memhogs running. Notice I got kswapd in this case now on 1. Notice I got IO8 here, and these are these GET requests. And I'm waiting to see if I can actually, how big did I push it? Let me do a memhog 100 gig. Now I'm not going to bring a PM chart at this point, but when we do hit this free, I still got 3 gig free, 2 gig. We're going to watch that get down to 0. They've only got 10 gig resident. By the way, I should warn you about this. I'm going to go to F. There's a field called swap. This is not what is out on swap. All that is virtual minus physical. I could have no swap configured at all and still have a swap value. I like to call that slop, S-L-O-P. If I malloc 100 gig but only use 1 gig, there would be, the swap would be the difference between what I allocated and what I reserved. There, we're at swap being 0 now, and my system time is starting to go up, and all of that is the killer. Let's see if I can catch this. Perf top. We did see killer before, but that was when we dropped to KDB and looked at things. Isolate free pages. Not seeing anything there. Let's do a D message tail. And we did have an Remember earlier, my varlog messages did not even show the It never got to it because of the memory pressure situation. But here, let's see, we killed a mem hog. And here's the score, the badness score. The workbook, I don't think the badness score is calculated the same way as in the workbook. The numbers are usually a little bit different here. And it's actually printing out the PIDs that are the targets for what it's going to kill, including bash. Remember, the parent inherits the children's badness. And so that's the shell that I fired up all the mem hogs from. And then you get all this stuff on a per node basis. And look at this by CPU. So you can imagine having 4096 CPUs and multiple ohms being hit. So here also is an ohm. Try to do a page fault. Tried to allocate pages and ran out of memory. It could not trim the slab or the cache any further, and it could not allocate physical memory or physical swap. I'm just looking at all this stuff. I'm not sure what the file RSS would be. I don't know what that is. That's something new. But I'm thinking it might be what it has in cache, but I don't know. Let's see. Okay, and we did actually see a kill here now of a mem hog.
That should just be file-backed pages as opposed to swap-backed pages.
Right, that's what I'm thinking. I'm just saying I don't know for sure what that was. Some of this stuff is new. So we were talking about this one here. Okay. So let's see, SAR-S, 1-4. So we are still swap used. SAR-big W, 1-4. And we see a lot of swap outs still going on. Now, I don't care about swap outs, it's swap ins that I care about. Swap outs can happen in the background, but swap ins are what I'm waiting for. I wonder, get delays. Let me do it as a watch. -D, -P. Oh, I kind of need a PID now. Let's see. Hang on a second. So let's try it with a PID. Watch, get delays, -D for delay, -P, the PID 31006. And look at reclaim time. I believe these are in nanoseconds. That looks to me like 326 seconds that it has been waiting for a trim. This is the memory trim. This is shrinking the slab, the buff mem, and the cache. But I'm not seeing any swap in weights. This is really, I have a PV on this one. This looks like it is a swap IO weight or a swap input weight, waiting for a page to come in from the swap. And ironically, memhog doesn't do any I/O. It's just a mmap and a write, but I am getting I/O weights associated with this thing too. And also CPU weight. And we had another kill. Now, if this were outside a CPU set, there would be much more severe impact with the out-of-memory killer. And another memhog that got killed. By the way, I think I mentioned it yesterday, if I put a -17 into it, it will not be a target for So PS-E, let's grep for array. The array D for MPT actually does that, cat/proc 5481/boom_ADJ, and it's a -17, which would protect it from You will not kill anything that's a -17. Let's see if that pressure is still going on. CPU set -Q. I have my own little script I wrote. I've got an RFE to get this capability here. That basically goes through, let me do it again here. Gives me a report telling me for each CPU set what it is, what it's contained, what its values are, and then what threads or processes are in that CPU set. And here's the one that I was just looking at, and notice memory pressure is kicking up on that one, but memory pressure is not doing anything on the other CPU sets. So by being able to do this, then we can find the PIDs. There are 4 PIDs that are in the CPU set that would then become a target for a kill. And then the daemon that's running an init.d type script or command would find the pressure, might even do some political checks and say, this is not a user that I want to kill, or this user is the one that's causing the swapping right now, let's kill it, rather than letting the kill it. Now, it should be killing what's in the CPU set these days. So there was a patch last fall that said, kill everything within the same CPU set rather than shooting everything on the system and just wildly killing things. So they're trying to get a little bit more predictability in the kill decisions. And that's why we were seeing memhogs being killed.
That memory pressure value, that is specifically a CPU set feature.
Correct.
What's the significance of the number? The number gets bigger, means there's more pressure, but what's the actual significance of the number?
I agree. Let's look at what it has here. Looking for the documentation on it. So here's what it's calling it. This memory section below has to be enabled. It's read-only. And then let's see where we have it here. Hardwall is not working. I'll talk about that Friday. Hardwall is always up. I'm not able to break out of my CPU set. Here's the memory pressure. The rate that processes in the CPU set are trying to free up in-use memory is what they're calling it.
Right.
Simple per CPU set running average of the rate processes are attempting to free memory. I don't try to take it as a literal number. I just use it as a red flag. And talking about load reduction, because it doesn't have to look at everything. It's reduced in large systems because it's doing on a per CPU set basis. Digital, all fancy stuff. Digital filter within the kernel tracks the recent rate at which processes attach, enter the kernel, direct reclaim code. And that's what we were looking at here. In fact, again, cat/proc/vmstats, and there was a reclaim in here. Scans, where was it? I don't want zone reclaim mode. By the way, I should try this, sar-b. No, sar-b 1space5, I don't think that's what I want. Sar-big B 1space5. So here's the swapping activity. Actually, this is just pages paged in, pages paged out. That, by the way, is what PCP was doing for disk IOPS. And then here are my page faults, and here's my swap. And then here's what we were looking at, pages being freed, and then here are the scans trying to find memory to recover. But I'm not seeing anything there right now. Let's see what -B gives me historically. And there we can see what MemHog was causing in terms of reclaims and stuff. But that doesn't seem to be happening right now. Yeah, the codes are finished. The MemHog is done on this system. I don't know if that answered your question there, Mike. Same thing with you, Carlos. Are we have any questions right now? So let's go back to the workbook. So there now I was actually creating swap IO. And again, because I was in a CPU set scenario, the swapping and the swap IO was not pressuring me in a different CPU set like the boot or the login CPU set. And if I don't have memory pressure in my CPU set, I have a better chance of keeping the shell and things like that in memory. So one thing that's missing, the Linux kernel should actually have a page cache floor, a minimum page cache size to say, leave a couple hundred meg open for my shared text and stuff. So this module is really doing the I/O, and I just did a quick demo there to identify if swapping is my problem. Earlier today we had swap allocation but no swap I/O. But then I put myself into a different CPU set on a different system and created swapping and *big W to show the swapping. Again, I don't care about the swap outs, it's the swap ins that I'm waiting for. You use top disk to monitor swap. And then we want to describe, and we'll come back to this Thursday, on how we handle memory shortage. And explain what kswapd does. Now, kswapd does not swap in, Mike. It's memory management and swapping out. And then the sysctl parameters. So first of all, you don't want to swap. It's not so much that you don't want to swap, it's the fact that if you're swapping, you're out of memory, which means your cache has been pushed to 0, and you can't keep shared text in memory. You can always add more memory, but adding more swap just means more swapping. But again, I got UV sites that are using the swap to throttle back the swapping and give lots of breathing room. It's going to impact the ones that are swapping, but those are contained within CPU sets, not impacting things in other CPU sets. And again, PBS Pro and Torque will create a CPU set for each job. And if you have to swap, try to get it off a root, but don't put it on home or something like that. Now again, a memory shortage could push everything out to swap, and these are not swapped back in until demanded. Yesterday I had a case where I had stuff out on swap, but there was no swap I/O, so I did a swap off and a swap on, and that pulled everything from swap into memory. So there are cases where I can see swap in traffic, what I call trickle swap. Small noise, which means head movement. I don't want my root device heads having to go to the swap partition for a couple of blocks, then having to go back to something that is production important. So there are times, and I've seen that quite a bit, where a memory shortage event a month ago, and now you've got plenty of memory, and you've had plenty of memory for the past month, but you still have stuff that's trickle swapping in, which are usually sysconfig or init.d daemons, things like eventmon d and ESP and web servers I often see out on swap, but I know of no way to know actually what's out on swap. So, swapping indications, we just saw that. Swap in shows up as IO8, that was the GET request. Look for kswapd, and we were looking at the WChan. A GET request is swapping in, sync page is swapping out. Or you can see that particular partition being busy. Also use *S to see that swap was busy, but that doesn't mean I'm actually swapping. That just means there's stuff allocated there. I could have unattached shared memory segments that are out on swap. And these unattached shared memory segments are never being used. They just never got cleaned up. *W gives me the pages swapped in and pages swapped out. So we were seeing pages swapped out, but not the swap ins. And we were also seeing with get delays the trim wait time, the reclaim wait time with get delays. Then I was trying to go to *B to look at a major page fault. That means I had to go to swap something in. But when I looked, we were at a swap out situation, not a swap in situation. And I did not do this one, but looking for pages being freed. And I was ignoring this right now, but paging, display, and swap display within PM chart. And then I also had bar log messages, and don't forget D-message. We even saw today where D-message showed a whole bunch of ooms that were not in bar log messages. The syslog daemon itself can get choked when there is a storm going on, things of that sort. Also, I didn't really look for it yet, but PMIE has a swap alarm capability too. And you can even have a pager set up ESP to see the swap alarm in bar log messages and set off your pager to say you're in a memory shortage situation. You can even write an alarm to watch pressure, to watch that memory pressure and say, oh, we've got a CPU set that's swapping. Do you want to intervene? So the main thing here, when you see kswapd and the number after it was the socket or the node number, I'm calling it the swap out daemon. It's the memory management daemon. It's going to free memory, and it's on a per socket basis. And by default, a socket is a node. When that node gets full, it's going to manage the memory on a per node basis. So somebody could have come along, generated an IPC or dev.shmem file that was all on that node, program went away, or maybe it got killed and did not clean up after itself. Now we've got an unattached, unused shared memory segment that has that node completely full. And then the CPU scheduler puts you on that node, but now kswapd is driving it crazy. And I was seeing this at a 2048 CPU system. I'll explain it later, but they were not spreading their page cache, and they were not spreading their dev.shmem to reduce the memory pressure. So they had, out of 128 nodes, they had about 30 nodes that were completely out of memory, and processes were still being scheduled there. And then they have to go off node for anything that they need. And even going to the other socket on the blade has an impact. So there's one kswapd per node. The number after it's the node that it's running. It runs within a CPU set. So the kswapd itself is within that CPU set itself. And again, we didn't quite see this earlier, and I'd never like to actually predict things. But what did we see earlier today? Let me go to a whiteboard here. So, kswapd wakes up on node full. What we saw today was a buff mem being freed first. But that's not typically what I'm seeing. But again, every kernel is a little different. I'm not going to guarantee this. After that, we then went to the slab. And in the slab, it was trying to reduce the directories and then the inodes. And again, this was based upon VFS underscore cache underscore pressure. Then we went to the inactive file page cache. Then we went to the active file page cache. And let me do it here now. And then we went to swap inactive anon pages. And then we went to swap active anon pages. and then, boom. Now, in the past, I've seen slab get hit before buff mem, but what we saw today was buff mem got trimmed right away. When we fired up those mem hogs and tried to push our slab down, the buff mem got trimmed first. Oh, and swappiness is controlling the balance between the inactive and the active page cache and anon pages. Are we okay with that? Can I go back to my slides? Okay. It's not bringing me back. What's going on here? There we are. I think I might have said directories and then inodes, but we can look at that more closely. In our example today, what we saw was directories because they were mostly directories. And again, what you'll often see is some sort of shrink routine in the WChan. Again, I am using a brand new 3.0 kernel for the first time, and I'm looking for differences there. So after the slab, then it tries to trim the page cache. It can't trim dirty or tempfs shemem, and the shemem can get swapped out. And that would include writeback and NFS unstable. This is incoherent data. We cannot recover that memory until they are coherent. So you can't trim that stuff. Again, we were just looking at the reclaim wait time with the get delays. And then after that, we start swapping out user pages. Okay. So this is an older release. I still don't have crash exactly working with my debug info, but here I happen to catch a kswapd that was in a trim, and here it's trying to balance pages across the system, but there was a congestion wait and IO_sched. That would show up as IO wait. And WChan would probably show a congestion_wait. Now this is not a 3.0 kernel, so there is a lab step to see if you can kick in and get crash working, but I got to work out the syntax for the crash command. I had problems with my debug info file. 2 parameters. Page-cluster controls the swap in request size. It's powers of 2, the largest being 2 to the 5th, which is 32. That gives me a 128 KB request size. That's the largest swap-in size I can do. If I'm going to stripe, I'm going to want a stripe unit size of 128 KB. Then the other one that Mike was talking about, it was a common workaround for ICE and stuff, and to prevent the from deadlocking. Older, particularly SLES 10 SP2, would actually deadlock, hang the system. And this commonly happens, and I'm still going to try to see if I can actually hang this kernel. So we were taking min-free kbytes as a workaround and upping that to like 128 megabyte. And there was a war on ICE for that to prevent. And again, this space, there will be a lab for you where you play with it. This space is not used by the cache, not used by the slab, and not used by anon pages. But it is used by the kernel for breathing room. In particular, I know some sites have to increase min-free kbytes for TCP stack growth. When they get short, bursty TCP stack growth stuff, the min-free kbytes, that stack is allocated in that area. And again, Mike, I bow to Hetty at any time in this area. He knows this stuff inside and out. There are a couple other here that I don't use at all, just mentioning that they're there. And I need to check on this, but I think, you know, in the older x86s, we had a fake memory addressing scheme for low mem and high mem, and that's what this was for. Metrics, sar-big W for pages swapped in and pages swapped out. And we were seeing that before. Again, I don't care so much about pages swapped out. It's when I need a page, when I take a page fault. So let's just say we jump to an address. And then look in the CPU TLB buffer. A TLB, translation, look aside, buffer, is a virtual to physical map. And this is known as a page fault or a TLB miss, meaning we ask kernel to look in the page table for a physical address. Now, a couple of things here. Worry about data strides. This is the rows versus columns. Fortran and C lay out their arrays differently in memory. And we want a stride 1 example. XY versus YX. I've got a good program example called matrix A, matrix B. The only difference between them is how they stride. And one is twice the time of the other because of the stride not being a stride 1, because of rows versus columns. So you want to fix the application first. Then we can also, that'll reduce TLBs, but we can also reduce by using huge pages and also super pages, which is an SGI thing.
We're supposed to be seeing a desktop there, Dave.
Oh, you're still on the desktop? I'm sorry.
Are we supposed to be seeing a desktop?
Oh.
No, okay.
You see *W metrics, and I'm typing in. I got some red there. Are we okay?
Yeah, fine.
You don't see what I've typed until I hit an enter at the end of the line. Okay? So I'm talking as I'm typing it, and then when I hit return, you actually see it. Moving on, though, we also have hub hardware support for TLBs. And that's something called the BAU, the Broadcast Accelerator Unit and stuff. So the hub itself is actually doing some hardware caching of TLB entries to keep track of them. We're trying to reduce the faults into the kernel to find a page address. Okay? Now, if no page table entry, no PTE, then allocate, usually first touch. If a PTE, then it's in memory called page cache. If PTE says swap, then we have to swap in the page. So anyways, when I take a page fault, I jump to an address or try to write to an address or read. I look on chip to see if I've got that virtual address this is also referred to as the MMU, the Memory Management Unit. which is hardware support for virtual memory machines. And by the way, Windows does all this too. So does Mac OS. So we look for the address in the TLB buffer on chip. If it's not there, that TLB buffer, we're looking aside virtual to physical. So if it's not on chip, then we take a page fault. That's called a minor, by the way, M-I-N-O-R. Minor page fault, where it's down here. This is a major page fault. So I take a minor page fault, jump to the kernel goes to the page table and finds the physical address. If it's not there, then we say there's no entry for this page yet. It has not been allocated. So this is the first time we're touching it, and then we allocate it on the node where the program is running. If we have a page table entry, then it's probably in memory, and we call that page cache. And if the page table says it's on swap, then we have to initiate a swap in, and that's known as a major page fault. Questions? Let me move on. Are you okay with this? Do you need any notes? Not hearing anything, so I'm going to move to the next page. So here's what we were seeing before. Pages paged in, pages swapped out. And again, I can have allocation without any swap I/O activity. I can still have a performance problem though. If everything that's out on swap is unattached shared memory segments, but I'm still out of memory, I'm still in a situation or still in a kswapd trim situation, but there's no swap I/O going on because everything that's been pushed out to swap is inactive, unattached shared memory segments. So you can still have a memory shortage kswap problem without any swap I/O going on. And then here's the one that I was just trying to get to. The notes that I gave, I was trying to describe this. So here's pages being paged in, here's pages being paged out. Here's a minor page fault, a TLB miss. All programs will take TLB misses. But again, how you stride through your data is relevant. Rows versus columns, a stride one pattern. Fortran versus C. And then you can also go to huge pages and super pages to reduce TLB misses. And then major page fault, in this case, I've got nothing coming in from swap. And then here's kswapd information. Now this is coming from that vmstats file, /proc/vmstats. So pages being freed, so that's my trim. So we're still trimming rather than swapping. There is still swap out going on. And then here's the scans. So this is basically the kernel doing the kswapd doing the scans or the kernel doing the scans. So this is the amount of pages that we're looking for, things that we can trim. And then these are the pages actually being stolen and being swapped out. And then there's an efficiency here. The efficiency says, what percentage of pages that I scanned? So look at here, 3531 plus this, let's see. So this is a good one. Add these two together and then take 3459, and only 2% of all these scans found a page to steal. The second one was pretty good though. 5,000 pages were scanned and 3,000 were stolen. So 57% of the pages that I scanned were stolen and pushed out to swap. Let's move on. So here, pages paged in, pages paged out, TLB misses, pages swapped in, number of pages placed on the free list, number of pages scanned by kswapd, and number of pages scanned by the kernel directly. I don't really know the difference between the two, we just add them together. And then number of pages the system has actually reclaimed. And then the efficiency was the scans, or steals divided by scans, is that right? Let's see, 50%. Yeah. Yep, that's the right ratio. So don't swap, reduce your process size, add more memory. If you're going to swap, do it away from root. And I don't mention here, but use CPU sets to control it. There was swap priority we covered yesterday. I used top-big O today to find those mem hogs. kswapd showed up in top and had a large CPU time with it. And you may see some W-chans that have a shrink to them. And then sar-W and top disk showing the swapping is high. And then we have the trickle swap-ins can occur for months after a memory shortage. Some documentation. So in lab, I just want you to play around a little bit, force swapping, to see if you can actually create an interactive performance problem. Use sar-W, this is what we did in demo. I did not use PM chart or top disk to monitor it. I saw it with sar-W. And then we did this earlier today, and I'm going to do it on Thursday again. I sucked up all my memory with the slab and buff mem, and then I tried to recover it with memhog. And understand what kswapd does. It's dealing with memory management. It's not actually initiating a swap in when I take a page fault. That's really not kswapd's job. The two key systune parameters, sysctl parameters, are min-free kbytes to play with and page-cluster. And if you up the page-cluster, you ought to, when you're swapping, you ought to be able to see the bandwidth increase as you do larger swap IO requests. And then also use sar-B to monitor things. Are we okay? I think I'm going to call it a day. Does that work for everybody?
Yeah.
It's been about 5 hours and I didn't want to push any further today. So tomorrow morning I do want to do a quick memory shortage situation. I don't know how quickly I mean when I say quick, but we need to move into the next module, sar-D and XVM tomorrow. So tomorrow is going to be, and RAIDs. I need to play with the sar-D and file system layout module, the RAID module, and the XVM module. And then Thursday will be XFS, and we'll be back to the page cache and the trim capabilities and those sysctl parameters. Plus Thursday we'll start with the dirty, the write back, and NFS unstable. And then Friday is just wrap up and CPU scheduler stuff. So if there aren't any questions right now, you're back to your own, managing your own time and deciding what labs you do. If you want me to take one of your systems and create a problem for it and you figure out what I did, go ahead and send me email and I'll create some load problems for you. But right now I'm not doing that for you. I'm just doing it on my system and looking at it as a group. So I'm going to stop the recorder now.